We are amazingly lucky to have the moon. The moon has a radius of 1,737 kilometers, giving it a diameter of 3,475 kilometers, about one-third the width of the Earth. But the moon is made of much lighter stuff than the Earth, having a mantle with a lot of aluminum and titanium, and a much smaller iron and heavy metal core. The mass of the moon is only 1.2% that of the Earth. But gravity is determined by the uniformity of mass, the density of an object, and the radius or distance to the center of mass. That is why the gravity of the moon is actually 1.62 meters per second squared, or 16.5% that of the Earth, which, as we remember, is 9.81 meters per second squared. To know the gravity relative to a point on the surface of an object, you have to know the mass, size, and shape, and calculate the effects of the entire mass from where you are to the center of mass. Your weight on Mount Everest is less than your weight in Death Valley, due to your increased distance from the center of mass. Many people think that gravity stops at the orbit of the International Space Station, but that is false. The strength of the Earth's gravity at 200 kilometers from the surface, where the ISS orbits, is about 98% as strong as that on the surface of the Earth. Astronauts float on the ISS because they are in free fall. Their horizontal velocity is high enough that they continually fall over the curve of the Earth. It's like being in an infinitely falling elevator. Gravity is still there, you just can't feel it. But with gravity on the moon's surface being only 1/6 that of the Earth, what could we build and launch successfully from a moon base? The SpaceX Starship is not really a specific design or ship, but a concept. Complete reusability for spacecraft for hundreds of missions. The Earth Starship is being rapidly prototyped and tested in southern Texas. Number 9 is on the pad and has undergone some testing. Because of its importance to our goals, I have started a new playlist called Starship Academy. As I start writing this early in the morning, I have a monitor permanently displaying the NerdleCam YouTube feed put out 24/7 by the NASA spaceflight crew. Please go over and subscribe to their channel after today's course. It is vital that all of us who love space science and exploration support each other. The Lunar Gateway is a concept developed by Boeing and others to justify continuing the development of the Space Launch System. It is a small space station to be placed in lunar orbit where astronauts will have to dock to go on down to the lunar surface in a lander. Many eminent space scientists, including Dr. Robert Zubrin, call it the lunar toll booth and deride its utility. It is in fact not needed to explore and develop a settlement on the moon. We have a space station in orbit around the Earth right now, larger than anything humanity will build for millennia. All of the resources are there, just a few days' flight from Earth. For an object as large as the moon, that used to be molten, the heavy elements will have migrated to the center and the lighter ones will float to the surface, leaving all that beautiful aluminum and titanium for us to use in our 3D printers. Other planets also have moons. It turns out that of the 8 planets in our solar system, 6 of them have moons. Only those closest to the Sun, Mercury and Venus, do not. The larger planets like Saturn and Jupiter have 53 and 79 respectively, giving us many future colony sites. Our moon has a mass of 7.342 times 10 to the 22nd kilograms and is only 362,000 to 405,000 kilometers from the Earth. It has an orbital period of 27.32 days with a synodic period of 29.32 days and an average orbital velocity of 1,022 kilometers per hour. It is beautiful in the skies of Earth and has inspired poetry as long as humans have existed. The names Selena and Cynthia mean the moon. The moon is also humanity's gateway to the future. The moon will be critical to our plans to explore and develop human off-world cultures in the solar system. Interstellar travel is far into our future, but we have hundreds of worlds to explore close to home. The moon will make this possible. Let's analyze what will be possible on the moon. Behold, Starship the Next Generation. All credit to Star Trek, please don't sue me. Built in the lunar shipyards and launched from the Armstrong station on the moon. The next generation Starship is twice the diameter and height of the original Starship, with a diameter of 18 meters and a height of 100 meters, with an internal volume of about 25,446 cubic meters. It will dwarf the Earth Starship, which has an internal volume of less than 3,181 cubic meters. The next generation Starship has been 3D printed from titanium alloy produced on the Moon. Titanium is rare on Earth, but the lunar regolith has a high percentage of light, strong elements. The Moon also has impacted meteors and asteroids under the surface that can be mined for iron, gold, platinum, and other useful elements. This thing could maybe launch from Earth with an extra super heavy first stage, but that's not why it was built. First generation Starships will bring explorers and colonists to low Earth orbit, where a next generation Starship will dock and load the passengers, cargo, and supplies. Since the Earth-launched Starship does not have to carry supplies for a Mars mission, it can bring about 450 colonists per flight, with an allowance of 250 kilograms per passenger with personal effects, giving a total mass of 112.5 tons. That would leave 37.5 tons for other supplies and cargo. Each of these people has paid $250,000 for the privilege of starting a new life. The rules are that whoever you were on Earth, you can have a new life off-world. Here in space, you will be judged not by what you have, but by what you can do, the knowledge you have, the skills you bring with you. How much you contribute will determine your status here. Since it will only cost about $2.5 million for Starship flight operations, the remaining $112.5 million helps fund the settlements on the Moon and Mars. Once the next generation Starship has taken on all passengers and their personal items, it undocks and leaves for Armstrong City, the main settlement on the Moon. There, the colonists will receive the training they need to either help support the Moon settlement or travel on to Mars. Mars is why the next generation Starship was built. Let's take a close look at the engineering and origins of this massive colony vessel. The numbers on Earth Starship have been changing as further development has improved and solidified the exact capabilities. Every improvement to the engines increases what it can lift to orbit. Every kilogram of launch mass saved means more payload mass. The Earth Starship, or Generation 1, now has a dry mass of 85 tons, a propellant capacity of 1,200 tons, and a payload to low Earth orbit of 150 tons, according to the latest figures I could find. This is much better than the earlier figures of 120 tons dry mass and 100 tons to low Earth orbit. This makes the gross mass at takeoff 1,200 plus 150 plus 85 for a total of 1,435 tons, with a propellant percentage of 83.6% and a payload percentage of 10.5%. This gives us a starting point for our next generation ship. The next generation ship would be twice as long and twice the diameter. We will want it to be hydrogen powered instead of methane powered because a large mass of water is available on the Moon while methane is not. Since our volume increases by a factor of 8, we can use this to start calculating mass. Here we see a cutaway of the current Starship. We will keep the relative dimensions the same. The volume of the fuel tanks can be seen to be about half the volume of the ship. The other half is payload area, seen here, and the engine area, seen here. The tanks right now have oxygen down here and methane up here. We will put hydrogen here and oxygen here, with header tanks in the same place as they are now. We want to keep the center of mass in the right place, and we'll probably need to adjust this common dome's location to account for the different relative volumes of fuel to oxidizer as we switch to hydrogen. Now let's calculate some mass. The increased surface area of the ship will be a factor in its mass, and steel alloy has a density of 8,000 kilograms per cubic meter. Titanium alloy is, however, only 4,420 kilograms per cubic meter. Keep that in mind. Since most of our mass will be in surface structure, we can imagine a cylinder 4.5 meters in radius and 50 meters tall, giving it a surface area of 2 pi r, or 9 times pi equals 28.27 meters circumference, times 50 meters height, gives 1,413 square meters. The skin of the Generation 1 Starship is at most 4 millimeters thick, according to an Elon tweet. That would be 0.004 meters. Multiply that by 1,413 and we get 5.65 cubic meters for the skin of the Starship, not counting the tapering of the nose. Multiply that by 8,000 kilograms per cubic meter and we get 45,200 kilograms of steel in the skin. So about 45 of the 80 tons of dry mass is in the hull of the first generation Starship. If we go with the next generation ship radius of 9 meters and a height of 100 meters, we get a circumference of 56.55 meters times the height, giving us 5,655 square meters. Let's go with a 2.5 millimeter thickness, as titanium alloy is stronger than steel, and Elon thinks he can get most of the Earth Starship down to 2 millimeters anyway. That would give us 5,655 times 0.0025 for a total of 14.14 cubic meters of metal for the next generation Starship hull. Now remember that the density of titanium alloy is 4,420 kilograms per cubic meter, and we get a total hull mass of 62,498 kilograms, or about 62.5 tons. Now 45 of 80 tons on the original Starship was hull mass. The rest was bulkheads, reinforcements, and other structural components, including wings, which our next generation Starship will not need. And assume the same ratio for our next generation ship, just to be safe. So we get 45 over 80 equals 62.5 over x, and solving gives us 111 tons. Let's round it up to 115 tons dry mass for our next generation Starship, just to be safe. You will notice that our much larger Lunar-made next generation Starship is not that much heavier than the first generation Earth Starship. That is the benefit of titanium and lunar construction. How much propellant can we store on our new ship? We calculated that half the volume of the ship was propellant tanks, and that the total volume of the next generation Starship was around 25,000 cubic meters. This gives us 12,500 cubic meters for propellant. We have decided to use liquid hydrogen instead of liquid methane for our moon-launched ship, and we know that the density of liquid hydrogen is 71 kilograms per cubic meter, versus about 424 kilograms per cubic meter for liquid methane and 1,250 kilograms per cubic meter for liquid oxygen, at minus 206 Celsius, or 67 Kelvin, where SpaceX likes it to be. We must keep our liquid hydrogen at or below 20 Kelvin. But we know from our last lecture that NASA accomplished this in the 1960s with a common dome and a little plastic insulation. Let's assume we can do the same. The ratio of the Saturn V second stage J2 engines was 5.5 to 1 oxidizer to fuel. Let's use the same ratio. Looking back at the relative volumes of the tanks in the Saturn V second stage, they don't look very different from what we have here in the Starship. We note that the volume of the liquid oxygen tank on the S2 was 310 cubic meters, with an oxidizer mass of 358 tons. The volume of the hydrogen tank was 980 cubic meters, with a mass of 69 tons. 310 to 980 plus 310 gives us an oxygen tank that is 24% the total volume of both tanks. So our hydrogen tank will be the other 76%. With a total volume of 12,500 cubic meters for propellant in our next generation ship, we get 3,000 cubic meters for oxygen and 9,500 cubic meters for hydrogen. Multiplying these by their respective densities of 1,250 kilograms per cubic meter and 71 kilograms per cubic meter, we get a mass of 3,750,000 kilograms for oxygen and 674,500 kilograms for hydrogen, for a total propellant mass of 4,424,500 kilograms, or about 4,425 tons. We add this to our dry mass of 115 tons and get 4,540 tons. Let's build the crew areas of our next generation Starship out of polyethylene for radiation shielding. Plastics like polyethylene have a lot of hydrogen and produce far less secondary radiation than metals, and absorb radiation much better. It has 3 times the tensile strength of aluminum and is 2.6 times lighter. It is 50% better at shielding solar flares and 15% better at stopping cosmic radiation. Let's put about 10 centimeters of polyethylene shielding on the outer wall of the habitat area, with spacers allowing 5 centimeters of water to be stored in channels between the titanium hull and the habitat area. If we assume the habitat area to be about 1/4 the total height of 100 meters, we get 25 meters. If we allow 2.5 meters per floor, we will get 10 floors. Polyethylene has a density of up to 970 kilograms per cubic meter. If we use 4 cubic meters of plastic, we will end up with about 4 extra tons of mass. This area also has water shielding, which would have a total volume between the plastic habitat and the hull of 71 cubic meters. That will add 71 tons for the water and 4 tons for the plastic, for a total of 75 tons added to our ship. But it will provide critical radiation shielding for children and young people traveling to Mars. $4,540 plus 75 gives us 4,615 tons. Let's allow 1,385 tons for crew, passengers, cargo, and supplies. That would be an incredible ship. Now we need to get this behemoth off the ground. But let's not name it Behemoth. Let's name it the Sagan. Since SpaceX flies the flag of the United States, this will be the USS Sagan. Now let's see if we can get it off the lunar launch pad. It has a mass of 6,000 tons, or 6 million kilograms. The gravity on the moon is 1.62 meters per second squared. That gives us a weight of 9,720,000 newtons. Remember, we are on the moon. It would be 6 times heavier on the Earth. Let's go for a thrust-to-weight ratio of around 1.3 so we don't break anything. We have no air resistance to worry about, and since the moon is a vacuum, we will get the best possible specific impulse. A thrust-to-weight ratio of 1.3 means we need 12,636,000 newtons of thrust. SpaceX does not have a Hydrolox engine. The most powerful Hydrolox engine flying today is the RS-68A from Aerojet Rocketdyne, used on the Delta rockets owned by United Launch Alliance. The A version has improved turbopump efficiency and more main injector combustion elements. We looked at the RS-68A on our Starship 1966 lecture, but let's review. The RS-68A is a Hydrolox engine producing 3,300 kilonewtons or 3,300,000 newtons of thrust in a vacuum. Some sources are a little lower, but we will go with this. The RS-68A can also throttle down to 52% thrust. Has a chamber pressure of a little more than 10 megapascals or 100 bar. Those of you paying close attention notice that I used 101,325 pascals as equivalent to a bar in the last lecture. As pointed out by the astute scholar Mark Zug, that is off by about 1.325%. A bar is 100,000 pascals. 1 atmosphere at sea level is 101,325 pascals. My bad. Thank you, Mark. The RS-68A was designed to be a simplified version of the RS-25 Space Shuttle main engines. The RS-25 was a staged combustion engine with 2 pre-burners powering low-pressure pumps and 2 high-pressure turbopumps. It was enormously powerful and efficient, but it was outrageously expensive and complicated. The RS-68 was a much more simplified engine. With 80% fewer parts and 93% less handwork, it didn't hurt so much to throw it away. The RS-68A has 2 turbopumps, but it is not a full-flow staged combustion cycle engine like the Raptor, or even a staged combustion cycle engine like the RS-25. Here we see the Raptor, running all the fuel through the fuel turbopump and all the oxygen through the oxygen turbopump. Here we see a schematic for the RS-25, having 2 pre-burners here, and 2 turbopumps here and here, with the fuel turbopump being expander cycle from the coolant shroud and the oxygen being fed from the first oxygen pre-burner exhaust. This gives the RS-25 2 low-pressure turbopumps and 2 high-pressure turbopumps. The RS-68A, on the other hand, is seen in this schematic. We see only the pre-burner here. A little bit of fuel and oxidizer is fed into the pre-burner, and the exhaust runs these 2 turbopumps, here and here. The exhaust gas from the hydrogen turbopump is vented overboard here, as you can see from this image of the engine. And the exhaust from the oxygen side goes through a heat exchanger to help pressurize the oxygen tank, and then is dumped overboard here in the diagram and here in the image. You can quickly see why this engine will not be as efficient as the RS-25 Space Shuttle main engine or the SpaceX Raptor, because it throws away propellant. The Raptor and Space Shuttle main engines do not throw any exhaust gas overboard. Everything gets burned through the turbopumps and combustion chambers in those engines. In the RS-68A, the liquid hydrogen fuel comes down here into the turbopump, then through this line to the combustion chamber. The liquid oxygen comes in here through the turbopump and then through this line to the combustion chamber. The combustion chamber has a regenerative cooling jacket which feeds back to pressurize the hydrogen tank. The nozzle is noted to not have an active cooling system, but is ablative for single use. This will have to be modified, as we want to use our rockets over and over. The RS-68A has this one preburner powering both turbopumps shown here and here. The RS-68A is otherwise a lot like the Merlin rocket engine produced by SpaceX. We see its diagram here. But the Merlin does have regenerative cooling. In the Merlin, a little bit of fuel and oxidizer comes into this preburner. It is burned and powers this turbine. The turbine is connected by one shaft to two turbopumps. It is a point of failure with this type of engine that the fuel and oxidizer run next to each other through these pumps with one shaft. Your seals have to be perfect or you can get an explosion. The oxygen turbopump, seen here, throws the oxygen straight into the engine, while the fuel turbopump, seen here, circulates the fuel around the nozzle and combustion chamber to cool them, and then into the combustion chamber through the mixing head. I think SpaceX could easily build a Hydrolox engine more like the Merlin, or go full flow stage combustion like the Raptor. We know the J2 flown on the Apollo program had a higher efficiency than the RS-68A does today, with 421 seconds of specific impulse and vacuum versus 410 seconds. Let's assume SpaceX can reach the higher efficiency with at least equal power. We need a thrust of 12,636 newtons for the weight of our next generation Starship, and we can produce 3,300 newtons of force per RS-68A. We will need just 5 engines to produce 16,500 newtons of thrust. This will give us a potential thrust-to-weight ratio of over 1.31, more than enough. We will put these in a quincunx structure like the Saturn second stage with the center engine fixed and the outer 4 able to gimbal. This is a very strong structure. And what would our delta V be? We have a total mass of 6,000 tons and a dry mass of 1,500 tons. We get 6,000 divided by 1,500 equals 4. The natural log of 4 is 1.386. Multiply that times our ejection velocity, which is 421 seconds times 9.81 meters per second squared, giving us 4,130 meters per second, times 1.386, for a total delta V of 5,724 meters per second, or 5.7 kilometers per second. Will this get us to Mars? The delta V to get off the moon and into low lunar orbit is 1.73 kilometers per second. The delta V to escape low lunar orbit and head out into space is 0.68 kilometers per second. And to escape Earth's gravity is another 0.14 kilometers per second. To get into a Mars transfer orbit, add 0.39 kilometers per second. When we arrive at Mars, a Mars capture burn will use 0.67 kilometers per second. Now we want to go to the Deimos station we discussed in this lecture. A Deimos transfer burn will use 0.34 kilometers per second, and Deimos capture burns 0.65 kilometers per second. Finally, getting into a low Deimos orbit requires 0.002 kilometers per second, and landing on Deimos only costs us another 0.004 kilometers per second. We can make it to Deimos station for 4.6 kilometers per second of delta V, and we have 5.7, a nice 20% safety margin. The next generation Starship will not have to be refueled in orbit 6 times. It can be fueled on the moon once and transport over 1,000 tons of equipment, supplies, and personnel to Deimos. From Deimos station, Mars-adapted starships with bigger wings can land the colonists and supplies on Mars to start their new lives. This is how you colonize Mars, by flying the titanium next generation Starship from the SpaceX Lunar Base to Deimos station. Thanks for listening. Don't forget to like and subscribe. Thanks to the generosity of Jake, this was recorded with a new very nice Yeti microphone. Thank you, Jake. I will invariably misspeak or miscalculate something during these lectures, and I always appreciate an opportunity to improve. Keep the feedback coming. Thanks again, and stay safe. Until next time, ad Astra Pro Terra.